this is important. This is actually the title of the stream. The reason why I've called it is Saving Lives because of this. We report the first case with missed cancer in a CNB detected by the system, which occurred immediately following deployment. The biopsy from a 55-year-old patient was diagnosed by the pathologist as benign. The second read system raised the alerts for the presence of cancer in 3 slides within the case with a high probability score for cancer, and the diagnosis was revised to minute foci adenocarcinoma. And what we are talking about today is something that is ridiculously complex, which I'm probably going to butcher to pieces, which is artificial intelligence. Something that a biologist should never really be speaking about because, well, we don't have the credentials for it, I think. So let me just switch the screens and get on with it. So this really came about because of a paper that I saw this week. This paper, in fact, entitled An Artificial Intelligence Algorithm for Prostate Cancer Diagnosis in Whole Slide Images of Core Needle Biopsies, Blinded Clinical Observation and Deployment Study. So this kind of struck home a little bit for me because in my professional career I've come across using artificial intelligence models not for prostate cancer diagnosis but for similar techniques and similar reasons that they're using it for. So I thought, well, why not go over a really, really great application of artificial intelligence and show people what's actually happening in the world today. This was published in August 2020. So it's very, very recent. It's the 3rd of August right now, so I think it was published, must have been on the 1st of August, or in preprint before. The paper's published in the Lancet Digital Health, which is a half-decent journal, which is pretty good, and it's a collaborative effort between people at the University of Pittsburgh, people in Johannesburg, South Africa, and an Israeli team as well. And what you'll find is that a lot of these kind of publications are collaborative works, and that's usually due to, say, a hospital being on one site, but the AI guys being on a different site, and so collaboration is required, which is really good. Anyway, so we're going to do the usual thing. We've got a little notes section here and what we're going to be going through in the next 40 minutes to an hour. And I've detailed some of the outlining bullet points, which you can see. So we're going to go through effectively what the problem is and why do we need an AI approach in tumour diagnoses or in cancer diagnoses. We're going to do an introduction into why that is, and we're going to look at histology and biopsy samples. We're going to talk very, very briefly about AI/ML, and then I'll detail what the publication actually addresses, and then the methods and results, and we'll go through them stage by stage. So it should be quite complete and quite informative. Got a bit of a sore throat, that's why I'm talking a little bit slowly, trying to be a bit more clear. But I don't think it's the Rona, but you never know. But I will be sipping on some water along the way. Watch out for that. Anyway, artificial intelligence, right? It's very buzzwordy. It's very hot. It's very hot right now. And sure enough, it's in constant development. The advances in AI are getting greater and greater. It's still a bit buzzwordy in the scientific community. I think people are trying to shoehorn in AI where they can in the biological sciences world, but there are certainly some genuine applications where it is absolutely required, and this is one of them. So we'll start at the top, right? The problem that we've got, and the problem that these guys in this paper stress, okay, is when you're trying to diagnose, in this case it's prostate cancer, when you're trying to diagnose diseases, generally you're relying on some sort of expert opinion from a doctor, a physician, someone that's been in the field for a very, very long time. And what's happening day to day is that tests are run. You'll either go in for a blood test or you'll go in for a biopsy, and a physician will then have to look at those results and interpret those results and then make a judgment. And that judgment can be quite profound. You know, if you're thinking in terms of cancer, you've got, you know, it really is life and death kind of decisions to be made. And many times cancer diagnoses are based on what's called a histology report. So throw up some images. So histology is a field of science that it's very old, I should say established rather than old. So let's just jump down here. I'll try and focus everything into the middle, get a larger picture. So histology is the study of tissues and tissue structure, and effectively it's image based, and histologists generate pictures, very pretty pictures like the ones we can see on the screen right now, right? And what's actually happening is that a sample of tissue, a sample of your body is taken in a biopsy, is punched out with a needle or a syringe or something, and then it's cut very, very thinly, incredibly thinly, almost to one cell kind of thick, and then it's laid on a glass, stuck to a glass slide, and then it's stained with certain chemicals that reveal its kind of structure and shape, and that's what we can see here. So the classical staining is something called eosin and hematoxylin, or an H&E stain, and that gives you this kind of pretty pink structure. So I think with the prostate biopsy, what actually happens is you can look away, gents. They don't go in through the mouth. They insert a needle into the prostate via the back end, and then they'll take a small section of tissue that they think might be cancerous, and then they'll cut that tissue very, very thin, and then they can stain it, and what you end up is a picture like this. Now, histologists and pathologists, the guys in the hospital, the clinicians, the men and women that do this, they'll make the diagnosis based on years of experience, and they know what a normal prostate looks like in this case, a prostate tissue looks like in this case, versus, say, a prostate with a cancerous growth in it. And they really rely on the fact that they are absolute experts in their field. They can look at an image like this and go, oh, top left is fine and the bottom right is cancerous, or the top left is cancerous, and they can effectively look at an image and call it. Now, there is an issue with that. For starters, you're going to get subjective diagnoses between physicians on this. It's just the nature of the beast. If one person looks at an image like this, they might say, oh, I think that could be cancerous. Or if it's not clear, say it's like the image is not that clear, what you might get is one physician saying one thing and another physician saying another thing, and then you can't decide. And that's a problem for the patient, absolutely is. So that's one problem. The second problem you have is, you are effectively at the behest of the ability of that doctor to make decisions and that physician to make decisions. Now, I'm sure that every physician will work to the best of their ability, but no one's perfect, okay? And when it comes down to your diagnosis, you want them to be perfect that day. And 99.9% of the time they are, but that 0.1%, they might make a misdiagnosis, for example, which could be quite catastrophic. So that's another problem. So you get like user fatigue, we'll call that. Another issue is that these aren't uniform pictures. You're thinking that, okay, so these four pictures actually look very different. But that could be because they're taken from different angles. Tissues aren't uniform all the way through. They're a 3D structure. So therefore, if you take the biopsy from a certain angle, then you might get a different structure than if you take it, say, from the top angle. And so that's another issue. So you don't get uniformity in the images. So if we go back to our little notes, right? So the problem that we've got is, and I'll highlight this in red. So you're going to have, first of all, subjective analysis, right, which isn't really what you want, right? Secondly, you could have doctor fatigue. Okay. Something else that you really don't want. You could have say ambiguous sample. So if your images just aren't, effectively, if you can't determine what the diagnosis is from the images, you might have resampling. It could take a very long time. Okay, so this takes lots of time, manual effort, and it's prone to error. Okay, so that's all of those are really not what you need when you have a life and death situation. Okay, so for years now there has been a drive to see whether or not we can actually get a machine, a computer, to analyze these images for us and then give a more robust diagnosis. And so that's what this paper starts to address, and they're using a technique called AI, or machine learning. So you've probably heard of AI, stands for artificial intelligence. It's this idea that a computer system is able to effectively, reason, act, and adapt, as they put in this nice little diagram here. And within the banner of artificial intelligence, you have something called machine learning, which is where effectively your machine learns iteratively and gets better and better and better at what it does. And that's the approach that these guys in this paper have actually gone through. So down here on the publication addresses, they've said the background. This is actually a really good layout for a paper. I recommend anyone that go to the Lancet, because their journals are actually really well written and actually easy to read, and usually open access as well, so anyone can read them. So they've actually put a background in the summary section. It says there is a high demand to develop computer-assisted diagnostic tools to evaluate prostate core needle biopsies, or CNBs. These are when they take the tissue from the prostate. But little clinical validation and a lack of clinical deployment of such tools. So basically there is a demand, but nothing's been implemented yet. And here they report on a blinded clinical validation study and deployment of an artificial AI-based algorithm in a pathology laboratory, words are difficult, in a pathology laboratory for routine clinical use to aid prostate diagnosis. So this is what they've started to address. Right. So let's talk about what they've actually done, because it's quite thorough. I think this is actually a really good paper, and that's why I wanted to bring it to people's attention today. So the paper starts with a general introduction around prostate cancer, and adenocarcinoma of the prostate is the second most common cancer diagnosed in men, with more than 1 million newly diagnosed cases annually. Okay, so that highlights just how much testing is going on. If 1 million cases are diagnosed, then how many cases are being assessed in order to get 1 million diagnoses? So that's very high. The tea tonight is just PG tips, nothing special. For most pathology laboratories, the current method for rendering a tissue diagnosis involves light microscopic examination of hematoxylin using an H&E stain tissue sections. So that's what we've just shown. This is an H&E tissue section of a prostate. Due to changing guidelines, there has been a dramatic increase in the number of core needle biopsies reviewed per case over the last decade. So one of the things I haven't mentioned is actually that they do multiple biopsies on an individual person in order to get a good sample size, but they will also do multiple sections and stainings of each biopsy. That leads to quite a lot of work, as you can imagine, right? So you've got, it just compounds everything that you're doing. Coupled with an increased overall cancer incidence and growing shortage of pathologists, this is something as well which isn't really talked about. There is a shortage of experts that can look at these kind of images, and what we can put that down to is the fact that it's one of actually the oldest techniques for assessing health and disease state and diagnosis. I mean, histology has been around for years, and what we're finding is that the average age of histologists is actually quite high compared to, say, new people coming through. There aren't many people that are taking up the task of being a pathologist as much as there used to be, and I'm not sure why that is, but it's just the way it is. Maybe it's not cool anymore. I think, you know, you get some absolutely beautiful pictures like this, which is fantastic. But in terms of diagnosis, it's actually quite a laborious task. Imagine looking over thousands of these images every day. You'd go absolutely nuts. And so they point out that they say there is an emerging need to develop automated artificial intelligence-based tools to support pathologists. Exactly. So that's what they've gone and done. And they talk about the research in context, which is really good of the Lancet to do that. Okay, so let's get on to the study design. So this is what they ended up doing. So they divide the entire publication up into 3 steps. Okay, so you have the development and testing of an AI-based algorithm. Okay, so we can think of the first one as development, or this generation, right? We'll go into that. We have, let's go back to this. Oh, I think this one. Development and testing of an AI-based algorithm, blinded algorithm validation in an external independent data set, and algorithm deployment. So let's talk about the algorithm development. Now, I'm not a computer scientist. I actually have a very good mate that is a computer scientist. So I've decided not to try and go into what was actually involved in the making of this algorithm, because I think there are far better people to talk about it than me. But what I will say is that they used a process called CNN, which stands for, I've been trying to find out what it is, CNN, which is a convolutional neural network. And in very, very basic terms, because that's all I can really give you, is it's a machine learning algorithm that is designed to be used on image analysis. And what it does is it aims to identify regions of images, and it will take those regions into context of where they are. So on this image here, you can see that it's got, this would be looking at like a feather, and it would build up the decision of what this picture actually is based on this spatial identification of all of these areas. Now, something that is really important with this is that it is a trained machine learning example, and we call that supervised. So we'll just write down here, just so that we've got it clear in our heads. The algorithm generation is the CNN, which stands for convolution. Is it convolutional? I think it is. Convolutional neural network. Yeah, let's get that right. Convolutional neural network. It is supervised learning. Okay. Now, supervised learning means that when you train this system, because you have to train this system, you give it data that you've told it if it's correct or incorrect. So effectively, it goes through rounds of training. and that's where the ability to become better, the whole idea around this machine learning algorithm to performance improve as they're exposed to more data over time. So the data is what you would call annotated. So, and we'll go through what that actually means in this scenario, but effectively it means that experts have looked over the data and gone, you've got that right, the machine has got that right, the machine has got that wrong, the machine has got right or wrong, and then that can guide the next learning stage of the machine, and you go through iterative rounds of learning. Annotated by experts. Supervised learning, and it's trained. Okay, so that's what we mean by that. So the paper starts with algorithm development. They talk about the fact that it's done on the algorithm is developed on a specific set of histological images, which is very common in this regard because you have to train it on a consistent data set. You don't want to give it that would be like trying to train an algorithm on detecting cars, but you've given it, a data set from an HD camera side on to a car, and then you've given it another image of, a car on the road at night with like a 1 megapixel camera. It's not going to be very good if the images aren't consistent that you build it with. So it's stated that, all of the pictures used were taken, H&E slides were stained, they were scanned in, they were all taken at the same magnification on the same microscope. They develop a CNN base, so convolutional neural network. And here's the important bit, right? So training is usually quite big. The training models were trained on 1,357,480 labeled image patches that were extracted from manual annotations on 549 slides. What that means is that they had 549 slides. They divided them into sections. Each image they divided into a section, and then they trained the image algorithm on each of those sections. And those sections of the images amounted to 1.3 million images. They talk in this paper about something called the Gleason scale, or the Gleason grade. This is just a grade of tumour that is used in prostate cancer diagnosis. So if you hear me talk about Gleason score, that just means it's a scoring metric that pathologists use for tumours of the prostate. So it says annotations were done by 3 senior pathologists, each with 20 to 40 years of experience. That's where the training comes in. So the annotation is done by people of experience. So you're setting the rules of the algorithm and you're training the algorithm with expert input, effectively. They go into some of the light maths of it. We're not going to get into that because I will probably get that completely wrong and look like a fool. So I'm not going to go into that. All right, so annotated by experts, and what was that? 1.3 million images we used to train. So that's, to me, that seems like quite a lot of images, but yeah, I don't do this kind of image algorithm genesis, so I don't know whether or not that's actually quite a lot. That might be a very small amount. Anybody that is a algorithm expert, please chime in and say, what are you talking about? So then they go on to the next step, which is the algorithm testing. So this is still done in-house. This isn't deployed out to the world yet. This is just simply in the lab that they are testing this algorithm. And they state, to evaluate the accuracy of the prostate algorithm, its output was compared with the ground truth on a large collection of whole slide images, independent from the training set. So there's a few things in here, right? So ground truth just means effectively the truth as determined by the pathologists. So if the pathologists say this is definitely a cancer, that's considered to be ground truth, right? So you compare the output of the algorithm with ground truth.